force on a moving charge in a uniform magnetic field. Okay, so here we will consider a magnetic field. Let's say it is acting along x-axis. Now, if let's say I consider a positive charge plus q, and if this positive charge plus q, it is moving with a velocity, let's say v, along this direction, such that this velocity makes an angle theta with respect to the field. So what happens here is this moving charge in a magnetic field will experience a magnetic force. So just like, when a charge is placed in an electric field, then that charge experiences electric force. Similarly here, when a charge is moving in a uniform magnetic field, or in general I will just say magnetic field, okay, then this charge will experience a magnetic force, and this force here it is F. What is F? Magnetic force. And this magnetic force, it has been found that it is directly proportional to the amount of charge which is passing through the field, the strength of the magnetic field B, and to the vertical component of this velocity. Okay? Because this velocity here, it is acting along this direction. So therefore, when you resolve this component into, when you resolve this velocity into two rectangular components, you will get one is v cos theta, which is horizontal component, and the other is v sin theta, which is the vertical component. So now this is the force which is actually experienced by a charge moving in a magnetic field. Now if I remove this sign, I will write with some constant. Let's say it is k, and this is q, b, v sin theta, where k here is a constant of proportionality, and in SI unit, this k, it is equals to 1. So if k is equals to 1 in SI unit, then this equation now becomes F is equals to q b v sin theta. Now please remember this equation, which is the force experienced by a charge moving in a magnetic field. Okay, now looking at this equation 1, okay, I can say that this force, when you write in vector form, okay, you will get q and then v cross v. So this is your equation 2, and this equation 2, it is the vector form of the force F, which is experienced by the charge q. Okay, because we know in mathematics, when I say AB sin theta, then this AB sin theta, it is known as the cross product of two vectors, that is A cross B. So similarly, because charge is a scalar quantity, so we cannot take that as a cross product. So the cross product in this case, look at this equation, we have B V sin theta. When I say B V sin theta, it means B cross B, but no. Though like here it looks A B sin theta. First comes A and then B, so I write A cross B. But now this is B V sin theta. Actually, I should have written B cross B, but I write B cross B. Okay, why? What is the meaning? Because the meaning here is, when you see A cross B, if I have two vectors, let's say this is a vector A and this is a vector B. Now if you say A cross B, that means you are rotating the vector, right, from A to B. You are going like this. Okay, and this is the angle between the two vectors. So A cross B means you are rotating the vector in anti-clockwise direction. So similarly, right, I write V cross B, there is a meaning for it. And this force here, okay, it is a vector quantity. So that is why it should have a direction. And the directions of this force, it should be perpendicular to the plane containing both V and B. Okay. Okay. So if that is the case, then this V cross B means you are rotating the vector from V to B in this way. So when you take A cross B, actually you will get another vector, let's say a vector C. And this vector C here, it should be perpendicular to this plane which contains both A arrow and B arrow. So similarly, this magnetic force which is experienced by the charge Q, it should be perpendicular to the plane containing V arrow and B arrow. Alright, okay, alright. So actually this force, right, to know about the direction of this force, then we use one rule which we call Fleming left hand rule. Okay. So what do this Fleming left hand rule says? So now let us look at this rule. This rule says like this. If I stretch my left fingers in this way such that the four fingers points the directions of the magnetic field, the central finger, it gives the directions of current, or I can say the directions of velocity, then my extended thumb will give the directions of the magnetic force. So with the help of this rule, we can easily determine about the directions of the magnetic force. Okay. Now, so we have seen that when a charge is placing in a magnetic field or it is moving in a magnetic field, that charge experiences a magnetic force, in which the magnitude of that force is given by equation 1 and the vector form of that force is given by equation 2. And please remember that this force, it should be perpendicular to both the planes containing V arrow and B arrow. Okay. After that, we shall see here about some special case. Special case. Case number 1 is when theta equal 0 degree. So what is theta? Look at figure. Theta is the angle between V and B. So when theta is equals to 180 degree, or I can say 180 degree. So first look at 0 degree. When theta is 0 degree means this is the field. So V also it is acting along the same directions. V also is acting along the same as the directions of B. So that is the meaning of theta equal 0 degree. So when theta equals 0 degree, what happens to this equation 1? Your equation 1, right, becomes F is equals to Q B V. Instead of sine theta, I'll write sine 0 degree. But as you know, sine 0 degree is equals to 0. So 0 into this will be 0. Okay. So please look down here. This case means when the charge is moving parallel to the field, then that charge will not experience any magnetic force because F is equals to 0. Similarly, when theta is equals to 180 degree, when theta is equals to 180 degree means if this is my magnetic field acting in this direction, then let's say a charge is moving opposite to it. That means the velocity it is opposite to B. So in that case, the angle between them is 180 degree. So again, this equation 1 becomes, when theta is equals to 180 degree, then you have the magnetic force F is equals to QBV sine 180. But as you know, sine 180 is 0, so 0 into this again will be 0. So therefore, we have seen here that when a charge is moving parallel or anti-parallel to the field, then that charge will not experience any magnetic force. Okay. Second case, when theta is equals to 90 degree, that means if this is the magnetic field, like this is the magnetic field, this is the moving of the charge, the directions of the moving charge. So when the field and the charge, or and the velocity you can say, they are perpendicular to each other, what will happen to the magnetic force? Whether the charge will experience any force or not. So let us see here. When theta is equals to 90 degree, your equation 1, F is equals to QVV sine 90 degree. And you know sine 90 is 1, so 1 times this will be QBV. And since this force is non-zero, so I say this force is maximum. So when a charge is moving perpendicular to the magnetic field, that charge will always experience a maximum force, and the directions of that force should be perpendicular to both V and B arrow. Okay, so this is about the, I can say the introductions of the magnetic force which is experienced by a moving charge.